Hi everyone, pleasure to be here. I am Ranvir. I'm the founder of Fitness Chain. In my past life, I did my PhD from Urbana-Champaign in Princeton, and I used to work in solving the blockchain trilemma. But this talk is about something else. It's not about scaling blockchains. It's about scaling the type of applications that can be built on blockchain. And the key to that is to build real-world apps on top of blockchains. And to do that, you require consensus on what happens in the real world. And the core to that is a protocol called proof of location, which I'll present in this talk. So in the digital world, the actual rare attribute is time. And blockchains fundamentally solve the problem of ordering events and hence achieving consensus on time. And that leads to a lot of applications that we see today, right? When you talk about the physical world, in the physical world, there is one more rare attribute on top of time, which is location. If you can achieve a global agreement on where something has happened or some asset is situated, you can actually invent a whole new class of applications that can be built that don't even exist in Web 2. I'll be going into the examples of that, but before, let me dive deeper into how to achieve consensus on location. So when you think of location, you can say that, oh, GPS already exists, why do I need a consensus, right? That's because GPS can easily be spoofed. Most crypto protocols use IP, predetermined location, but that can be spoofed with VPNs. You can rely on local beacons for determining your location, but local beacons can collude. So the solution here is to rely on a global set of nodes to do active measurements on where you are situated and aggregate them. Well, if you rely on a global set of nodes, those measurements have to happen over internet delays. So that's a solution, but there are a lot of challenges if you want to solve it this way. Let's say there's a prover named Waldo, which wants to prove its location. Our watchtowers, which are these internet-based beacons, want to determine the location. Now in this setting, you can have malicious actors everywhere. Waldo, the prover, wants to spoof its location. One of the watchtowers, which are all decentralized, might be malicious. On top of that, internet does not follow a constant speed of light. So you have to learn the manifold of delays to distance over the internet. So based on that, we resolve proof of location into two core parts. One is you have to, first of all, understand the internet's geometry. Like if my ping delay to a certain node is 100 milliseconds, what does that correspond to in distance? And on top of that, you have to build some sort of a quorum in 2 dimensions to triangulate based on those distances. You need a quorum because actors can be malicious. The first part, determining internet geometry, happens by all the watchtowers, which are challengers in this protocol, measuring delays between one another. This will form some sort of a time matrix. Now, a lot of entries in this case would be Byzantine, and we can rely on the fact that this matrix will have a very low rank because it's essentially corresponding to 3 dimensions, right? And you can use that to actually complete the matrix by utilizing standard robust matrix completion techniques to rule out Byzantine measurements itself. Okay, so now utilizing this, you can have an actual understanding of the manifold of the internet. Now you have that, you can convert these times to distances, and then you can apply intersection, right? That's standard trigonometry, but with a slight twist that you need the trigonometry itself to be Byzantine fault tolerant. So we invented a whole new class of trigonometry called Byzantine fortified trigonometry, BFT, to achieve that quorum. And once you have that, the intersection region becomes the provable location. It can no longer be spoofed, and there's a heavy amount of security attesting to this. So this is not just theory. I can link you to the paper. There's actually an implemented system with over 6,000 nodes and $8 billion worth of cryptoeconomic security in ETH, which is securing this protocol. Now, like, how do you use this, right? So you want to build something in the real world. You need what are called physical world APIs. So these are like data that don't sit on the internet. It doesn't sit on chain. It sits on the physical world. How do I know if something happened in the real world? Require three things to observe anything. First, you require a sensor to collect real world data. And you need a proof that your data is coming from a sensor and it's not artificially generated. Luckily, each one of us carries that sensor in our pockets called a phone. And most phones have trusted hardware that can be utilized to prove that the data came from a camera sensor. The second core thing that you need is you need verifiable location. And that's what proof of location solves. And the third thing you need is verified timestamping, which is what all blockchains essentially do. And using that, you can actually request observations in the physical world at places you are not present, right? So you can have an AI say that, hey, what's happening at this event in East Denver? How many people are present at this event? And you can achieve global consensus on that based on this. So you have the actual observation that's captured by, we have an app and an SDK to manage it, supported by proof of location and timestamps. You can utilize these observations to actually actuate or do things in the physical world. So you can have protocols that can instruct humans to carry out certain amount of actions. So think of this being eyes and arms of some agentic AI, which is sitting anywhere, right? It's global eyes and arms. So we have to be careful here, but I think we will have sufficient security practices here. To do that, it's essentially simple. An observation is a state at any given time in the physical world. And if you know the initial state and the final state, you can figure out what changed in between and what action was performed. So in this case, in these two images, there is like a tree in the second image, where it's like, oh, somebody planted a tree there. So you can actually actuate. Utilizing this, you can build like whole new class of protocols. At the very basic, you can build verifiable news, right? You can actually have physical attributed NFTs, right? So, or coins. So let's say you're doing a token distribution, you can actually geo-bucket your token distribution if you want and prevent all sorts of airdrop farming and sniping. You can build actual insurance agents, which would actually audit and reduce risk for real-world insurance. It can be used for infrastructure deployment. You can use it for DPINs and even like physical infrastructure, right, roads. And you can build classical things like MEV resistance, because once you know location, you can compensate for the location in MEV. That's it for my talk. If you want to learn more, you can go to our website, witnesschain.com. It has links to all of our paper. All of these are like proof of location is a research paper. We have presented in a lot of journals. You can actually interact with this system by downloading our app, which is in invite only. But I'd like to invite you all to try out this app. And yeah, you can follow me on Twitter if you want to know more. Thank you.
Lovely, thank you. Fantastic presentation. Do we have any questions from the audience? Oh, okay. Yes, over here.
Hey, thanks. So I think most like impossibility results that I know of in proof of location, they have to do with multiple attackers at different points trying to spoof one location. Is that something that your proof of location protocol addresses, or?
Exactly, that's a great point. So in a lot of proof of location protocols, you rely on local beacons, right? And if you rely on local beacons, the amount of nodes you can select for proving your location is limited to what's in your line of sight. And if that's the case, you have only limited number of nodes which can be colluding, or you can corrupt them very easily. But since proof of location happens over the internet, the amount of nodes that can ping you is the whole global set of 6,000 nodes and growing. And to corrupt all of them requires a lot of effort.
Yeah, very interesting. Thank you.
Thank you very much for that. Any other questions? Okay, but I just had one question with regards to the sort of ETH staking element. So I presume you're using ETH security for this, or
Yes,
can it
it's,
be applied to other chains as well?
Yeah, it's. I mean, right now we are the initial AVS to launch on EigenLayer. So a lot of our security comes from ETH on EigenLayer, but this is kind of agnostic to like what you use as an underlying stake for all of these nodes. It's just that ETH is the most kind of programmable and stable simultaneously. That's why we chose it.
Fantastic, lovely. Thank you very much. Another round of applause there, please.
Thank you, everyone.
We're going to move into